Evening. Thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. Where tonight we're going to take a look at a peek inside the 2025 AP Calculus exam. My name is Mike Houston, and I'm the moderator for this event. I teach algebra, calculus, and statistics near Pittsburgh, where I use TI technology to make tough to teach, tough to learn concepts accessible to all my students. And I'm super excited to be joined by our two panelists tonight, Dennis Wilson and Tony Record. Dennis just entered his 30th year of teaching at Landmark Christian School in Fairburn, Georgia. He's the math department head for his school and teaches honors pre-calculus and AP Calculus BC. Dennis is an active member of the Georgia Association of Advanced Placement Math Teachers, and he was an AP reader for 8 years. He loves using TI technology to help students connect mathematical concepts using visual representations. Dennis, it's great to have you with us.
Thanks, Mike. It's great to be here. Hello, everybody.
And Tony has been a math teacher at Avon High School, which is a suburb of Indianapolis, for the past 35 years. And for the past 25, he has primarily taught AP Calculus and has worked to build his school's AP Calculus program to nearly 300 students. In addition to being a T-Cube regional instructor, Tony is an active consultant with the College Board, having produced several AP Live and AP Daily lessons and trained teachers in 27 different states. He has authored the AP Calculus AB curriculum for the KIPP charter school system across the United States and is currently writing the AP Calculus curriculum for the Department of Defense Education Division to be used in schools linked to American military bases around the world. He also serves as an AP Calculus consultant and question leader for the College Board. He lives in Avon with his wife and two teenage children, and in his spare time, he loves to play guitar and is active with Central Indiana's Hendrix Civic Theater, having appeared in several productions. So, Tony, I know you're feeling a little under the weather, but thank you for being with us tonight.
Thank you so much, Michael, and welcome everyone, and welcome to another exciting school year.
All right, Tony, kick us off for tonight. What can we expect? What are we going to do tonight?
Absolutely. Well, what we're going to do is just take you on a brief tour of the 3 calculator active free response questions from the 2025 administration of the exam. I'll do just a small sort of snippet of some of the scoring guidelines, some of the nuances that have been sort of baked into the reading this year that might be a little bit different from previous years. And as we work through those 3 problems, AB1, AB2, and BC2, Dennis is going to do some fantabulous calculator sort of interaction with those particular problems and show you how you can really make those problems come alive to the students that are in your classroom. And then I think there's a rumor that we're going to have a webinar drawing, right? I think at the end of the cast today.
Thanks, Tony. And Dennis, what can we be able to expect to be able to do by the end of the webinar tonight?
Hopefully by the end of the night, you can say to yourself that I can understand key takeaways from the 2025 AP Calculus reading, and that you feel like you can have your students prepared to use the calculator efficiently when the AP exam rolls around in May, and that you can use TI technology to teach consistently addressed topics that we see every year on the exam. And finally, that you can use the mathematical practice that are in the course description in your teaching and to reinforce them using TI technology.
Thanks, Dennis. So tonight, some of you have already realized we're using that chat window to send your own messages. Some of you are saying, hey, here's where I'm joining from tonight. And I personally always love to see that. So thanks to everyone that had a chance to do that. As a reminder, this is being recorded and we'll provide a link to the event certificate of attendance at the conclusion of the webinar, along with all the files. And we're talking both the TI-84 files and the TI-Nspire files, files for both platforms at the end of the webinar. So hang tight. This is going to be a lot of fun. And without further ado, Tony, it's all yours.
Okay, let's take a look at this here. You always want to make sure that you're going to display on the right window here. Just give me a moment.
Tony's fancy and has multiple monitors.
And you know, it does me no good, as you can see. It's the monitor during rehearsals switch to another one. But in any event, we're so happy to be with you here, and we're going to go ahead and just take you through a quick little walkthrough of a few problems. The ones that we are talking about are indeed the calculator active questions. So we're going to start off with ABBC1. It's a problem that I have a little bit of familiarity with, having served as its question leader. And then we'll hop on over to AB2, a little bit to do with some volume and some area. And we really hope that we have some time to spend a little bit with BC2 for those of you that do teach BC. Dennis has this wonderful activity that I'm dying to take a look at again there with that particular problem. So here we go. Before we start, I want to talk a little bit about some information that was provided for those of us that were involved with the reading at the open forum back in June, and that the scoring philosophy is changing just very subtly as we move into the 2025 reading and beyond. And we're going to throw these words out to you this evening: entry points versus dense points. And I'm not going to be able to go into the grave detail that I would really like to do, because it could probably take a whole hour-long webinar to do that. But I want to get you just used to these particular pieces of terminology, and certainly encourage those of you who might be thinking of attending NCTM later in October down in Atlanta, or maybe possibly some of the other national-based conferences throughout the United States, to attend the forums that are going to be presented by folks like Stephanie Ogden and Sharon Taylor, the chief reader, so that they can go into a little bit more detail about this. But ideally, we want a question and its scoring guidelines to capture data across all, and I'm going to say the 10 available points, because we have a scoring rubric that sets from a 0 to a 9 for each particular problem. And what we've noticed here in the past is, let's say we have this particular problem. This is data from a problem not so long ago, not a particularly good problem per se, at an average of 3.14. But we see that over a quarter of the students scored a 0 on that problem. Now, that doesn't necessarily mean it's a bad problem. It doesn't necessarily mean it's just a really weak year for students. But what it does mean is that we're going to have a really difficult time capturing data when we only have 75% of the population who scored points, and then we've got to sort of pack them into bins that might indicate that they scored a 5, a 4, a 3, a 2, etc. And it's very likely that some of those 25% who scored that 0 may have gotten a 1 on the exam. We never really know. But what is possible is that some of those points that were not earned among that 25.2% population might have had some pretty good calculus in them. And maybe they were just a little too dense. And if we kind of think of them more as entry points and sort of back off on some of the requirements, we might be able to get a little bit better data out of that particular student. And then again, we can see another situation here where not as many students scored a 0 in this particular problem. We had a little bit better mean. But as you can see, our bars are sort of up and down and up and down. And with this particular situation, it's very likely that students who earned a 6, 7, 8, or 9 on this problem probably earned a 5. So then that only gives us a 5 on down to figure out who's going to earn the score that would be a 1, 2, 3, or 4 on the exam. And so these two situations just kind of give us a little bit of convoluted data. And we would like to try to sort of improve upon that a little bit. And so our goal is, you know, the implication of less dense points means that earning a point would indicate success on what the College Board and the Test Development Committee have decided to assess. It doesn't mean that the response is perfect. And it's also really important that we understand that we're not doing away with rigor. The College Board is not going to do away with communication all throughout the free response. They're just going to find those times when we're going to award students for knowing the calculus without being necessarily perfect. So hopefully that kind of describes it a little bit. You'll see some good examples here in just a moment, especially with our first problem. So this is ABBC1, the invasive plant species. To kind of expedite things, I'm just going to read each individual part. But Just to highlight the problem, we had a function defined with this arctangent that modeled the number of acres in a fruit grove that affected by the species T weeks after the species appears. And we also know that C prime is equal to this rational expression, which maybe Dennis might talk about a little bit later when we get into the calculator, but it's kind of interesting to look at that, thinking that maybe we don't want to necessarily favor students who have CAS, and we're going to provide the derivative of that C of T for all students to be fair and equitable. So part A asks to find the average number of acres that were affected by the invasive species from time 0 to time 4, and we must show the setup for the calculations. So the scoring guidelines looked a little something like this. We have our 1/4 times our integral C of T from 0 to 4 with respect to T. That is our beautiful average value formula that we're looking for so that the student would earn that first point. And then the answer is going to be obviously performed using some technology. It's very likely our students aren't real comfortable integrating the arctangent by hand. And so that would serve as that second point. And so if we just look at some of the scoring notes here, and which are sort of an abridged version of the scoring notes that you are all, as calculus teachers, going to receive eventually. So I know that might be one of the first questions is, hey, how do I get my hands on this document? Well, unfortunately, we can't share this with you immediately. However, you will be getting a document, a pretty robust document from the chief reader in the form of the chief reader report, and it's usually going to be done at the latest by the middle of October. Now, don't shoot me if it's a little bit late, right? But that's about the time when we can expect that document to be out, and it's going to have all of the information that you see on these slides and more. So as you can see from these scoring notes, what I find somewhat interesting right here is that the student could do something that we normally didn't like in the past, right? We are dividing by 4 sort of through our stream of consciousness to get our correct answer. Or in the case over on the right, even worse, right? We have the correct answer and we have the definite integral set up with this horrible linkage error. But it turns out that both of these solutions would earn P1 and P2 despite this linkage error. That might be a really good example of what is referred to as an entry point. This student certainly knows their calculus, and it's very likely that they, and Dennis, you can chime in, but maybe a student typed in the definite integral into their calculator and got that 11, and then probably what? Divided by 4, you think?
Yeah, they put it in multiple lines in their calculator, and those multiple steps became pieces in that expression.
Yep, I totally agree. And yet it's still good calculus. It may not be the best communication, but there's going to be a time and the place later on in the free response questions where we're going to, and by we, I mean the College Board, it's going to be just a little bit more persnickety about some of the communication.
So
Now,
Tony, I know
yeah,
in the
go ahead.
past, linkage error is a common loss of a point. What about a copy error on a problem like this? If they resolve with the right answer, how does that handled?
Yeah, typically speaking, if they resolve to get that correct answer, things are going to be okay. You're going to see, I think, an example of that maybe in our part C. So when we're definitely dealing with that entry point genre of part of an FRQ, some of those things like the linkage error, the copy error can be overlooked. And in some cases, some scratch work that might not be truly calculus and mathematically sound could also be overlooked. So that's a very good point. And in part B, we're going to find the time t when the instantaneous rate of change of C equals the average rate of change over the intervals 0 to 4. And we need to show the setup. So this is going to be another 2-point question. And one of the things that we were looking for is the student using the average rate of change. Now you'll see in a moment that there's several different ways that that average rate of change can be presented. And it will require some technology, of course, to bring about that average rate of change because of our ugliness of our C of T, arctan function there. Of course, we want to make sure that the students are in radians. It's kind of written all over the test, and that's going to be very important. And then for the setup, we're going to take the derivative of that C, which was given, and set it equal to that decimal 1.282, resolve that with the calculator to get our 2.154. And so there's going to be 0.3 and 0.4. And our scoring notes are going to indicate that that third point, P3, can be earned by presenting the expression for the average rate of change, just presenting it. Now, that can be presented in a variety of ways. And for those of you who've sort of been around for a while, you might remember that average rate of change is always needed to be presented by a difference quotient, as you see in our first two examples here. But note, because our t value is 0 and our c of 0 there was also 0, either of these two would be perfectly acceptable. The students did not need to put the minus zeros after those two expressions. And then if you look at our fifth option, well, that one's kind of interesting, right? The definite integral of c prime, which is going to result in our c of 4 minus c of 0. Now, I am missing something here, and I noticed this. There should be a 1/4 in front of that, right, to bring about our 4 minus 0. So that's going to be really important. We need to have that 1/4 in front of that as well. And of course, P4 is going to be earned for the correct answer, supported by that equation, the C prime. Now, before we move into the part C and D here, I just want to say something about this linkage error and the things that you've seen so far that maybe you might not agree with. Remember that you are the one who sets the guidelines in your classroom, right? Just like a lot of my colleagues I know here in the presentation, we're going to raise our bar high. And I would encourage you to do that. If you don't want your students to commit linkage errors, then go ahead and enforce that. And typically speaking, if you get on top of that pretty early and students see that they can be penalized for such things, they're going to be more apt to not produce those linkage errors as time goes on. And in the event that a linkage error could carry some kind of an issue on the AP exam, they're going to be ready.
Tony, I'll just say that one thing that's helped me with linkage errors is having that conversation with the teachers who are feeding me students, having that vertical idea that students need to have a good exposition, a good communication of the problem, and just getting our teachers to reinforce it, making things that are equal, and letting them see that importance as they pass them on to you. It's been huge help that I don't spend so much time on communication later.
Yeah, that's a great point. And that's a great time to do that is with in your PLCs. See if you can do some sort of crossover and going to those Algebra 2 teachers if you don't teach Algebra 2 or those pre-calc teachers. So good point there. And in part C, we're going to assume that the invasive species continues to spread according to this given model for all positive times t. We want the students to write a limit expression that describes the end behavior of the rate of change. Evaluate that limit expression. Now, the key here for this first point you might find very interesting to earn P5. The question very specifically asks to write a limit expression for the end behavior of the rate of change. So that's certainly the C prime. However, what if the student wrote a limit statement that involves C of t? Think about that. Should P5 be earned? We'll get to that in a second. Now, of course, this particular limit that we want is not too terribly difficult to solve. Remember, the students do have a calculator active, type of question here so that they could use their TI to either graph this or maybe even use CAS, or if they just are very on top of their game, they can see that the degree of the numerator is much less than the degree of the denominator, which is going to result in 0. Now, getting back to that question, P5 could be earned for the limit of C of t. That does not have to be the case in your classroom, and I probably would enforce that a little bit more stringently in my classroom. But the philosophy with this entry point is that we want the students to understand end behavior. End behavior is more focused on that t approaching infinity in this case. Now, if the student uses C of t, they're not going to be eligible to earn P6, obviously. And then you may have heard some stories about not sort of demonstrating or modeling arithmetic using infinity in front of your students. I don't like to do it. I tell my students infinity is not a number. Therefore, the rules that govern arithmetic will not apply to infinity. But so many students would write a statement like this that certainly would lead to the correct answer. So we would consider that in this particular problem as scratch work, and it would not be considered for scoring. but we have to understand there could be some other issue down the line, maybe next year, where working with arithmetic and infinity could not be such a good thing. So again, keep your bar high. And then finally in part D, a little bit more robustness happening here. At time t equal 4 weeks after the invasive species appears, measures are taken to counter its spread, and this brand new function marches into town, a of t, that has this sort of function defined as a definite integral vibe. That's going to model the number of acres affected by the species, and the time interval from 4 to 36 is being used here. We're asked to find at what time does A attain its maximum value. Justify your answer. And we're really hoping that students look at this as a global maximum. And so obviously the scoring guidelines here are going to be a little bit more intense because we do have 3 points still available. P7 is earned by just simply considering the derivative of that A having to be 0. They don't necessarily have to compute the derivative like you might see on this first line. Simply the sentence A prime equals 0 would be enough to earn that P7 because we see that the student knows that the derivative equaling 0 is the jumping off point. Now P8, that was the most difficult point to earn on this entire problem because as you can see, that represents the wonderfully crafted table of values via the candidates test. Note when you do a candidates test, it's very important that all the values are correct on both sides of the column. Now on the A of T side, we don't necessarily need to see this many decimal places. In fact, one value to the right of the decimal would suffice because we're not looking for those values specifically. So the 3 decimal place rule is not in effect. And then, of course, somehow an answer must be crafted that does state that that maximum value does occur at t equal 11.441 or 442. Now, just a really quick rundown with the scoring notes. As we said, P7, pretty much an entry point. We could call it that. We just need to state that A prime is equal to 0. Note, A prime changing signs is equivalent to saying that A prime is going to equal 0. Now, to earn P8, a candidate's test would be beautiful, but there are other ways to present a global argument. One of those is to state that t equal 11.441 or 442 was the only critical value on the interval, and then go on to state the sign change. Or we could state that A prime was positive strictly on the open interval 4 to 11.442, and A prime was negative on the interval 11.442 to 36. That sort of gets us in our interval, describes all of the behavior of A prime, and thus gives us that global argument that we need. A response that presents a local argument cannot earn P8, but it certainly can earn P9. And trust me when I say a lot of students opted for that route. And so as you can see, the average on this problem, the global mean 3.3, that was for the AB students, and 5.2 for the BC. 3.3 was the lowest of the 6. I don't know if I should have a complex about that as its question leader, but I do know that last year I was the leader on ABBC1 and it had the highest mean. So I guess I balanced things out over those last 2 years. But
Can I
it
ask a
was,
question
yeah,
there with that
absolutely.
mean then? One thing that I noticed different about number 1 this year is typically we're given the function as a rate. And this year they gave us the quantity. Did that trip some of the students up?
I think so. I certainly think so. And the sort of those hidden words, that rate, that word rate, especially in part C, it was very easy for the students just to see the C of t as the first presented function and use that in lieu of the C prime. So that's a good point. So, Dennis, what do you got here on the calculator for this one?
Well, I think one of the things that we want to make sure that our students do when they enter the exam is that they're prepared to use their calculator for the question. And so we'll start looking at the TI-84 first, and you can see that I have here the TI-84, and you might say, oh, he didn't even get ready for this question. But what I want you to think about is your student is coming out of a multiple choice test, and their calculator has been doing all sorts of things. And so I've got a function here. Tony, can we see my screen?
Yep, it looks good.
Yep.
Looks
All
good.
right. So we've got the TI-84. You can see that the student has some function in here, the y equals, and they've got the graph. And one of the things that I like to equip my students with is what's called a graphical database file. And so if the student has this loaded, I'm going to press second program and move over to the store menu and choose recall graphical database. And I'm going to recall graphical database 0. And so all my students 84s have this. And what it's going to do is, I want you to see, it got rid of my y equals, and it changed me to the zoom window I prefer. And I've got the axis there. And so it's really nice. The student's starting with a clean slate for this question. And so the first thing on an 84 I want my student to do is to go ahead and define that function in the y equal window. So we'll go into y equals. And what we're going to do is put in C of t for y1. So 7.6 arctan 0.2, and of course we're graphing a function of x there. And so there's my C of t. And what I encourage my students to do is, once it's defined, to go ahead and graph and look at the graph and try to have an understanding of what that graph is telling us about the problem. So before we do, I want to think about that window. And if a student reads through all four parts, A through D, they see that we're talking about times from 0 to 36. So I want to be very careful not to just randomly press the graph button. I don't want to waste time looking at a window I don't want. So I'm going to press window, and I'm going to change my X min to 0 and my X max to 36. But instead of pressing graph here, I'm going to go to zoom, and I'm going to choose zoom's fit. Zoom fit is 0, and it's good that your kids know what zoom fit is. What it's going to do is going to take that X range from 0 to 36 that I have, and it's going to fit those Y values in. And so there is our graph of C of t from 0 to 36. And we can see that the invasive species, that the number of acres, it's starting down there at 0 and it's working its way up. But what's also nice here is that we're seeing that it's starting to level off. And if C of t is leveling off, we know that its derivative is going to get smaller and smaller and head towards 0. So just looking at the graph on the range that we have, we've already got an idea of what the answer to C will be. So first thing we did was find the function y1. We've graphed that function. Now I'm going to go to the home screen. So second mode to quit and go home. And Tony talked a lot about that communication and keeping that bar high. Today, I did a lot of easy problems in calculus. And I said, hey, we're doing easy problems because what we want to focus on is telling the story with our calculus. We want to communicate our thinking step by step. And one of the things that we do is, when technology is involved, is I want to make sure I model that I want to model that structure the same way with my calculator. So I'm doing an average value. I'm going to do alpha xt theta n to get that nice fraction template. And then I need an integral there of C of t. So to get that integral, that's math 9 for the integral. And I'm going from 0 to 4. And I'm going to put in y1. So to get y1, we have that shortcut alpha trace. Alpha trace brings up those y variables, and I put y1. Now, here's a word about communication. When I'm teaching calculus, when I'm making sure my kids understand calculus, I would put parentheses and open up set of parentheses and put x in there so they understand y1's a function of x. But once it's exam time and we're prepping, I'm just going to go ahead and leave y1 there to save some strokes. It will treat that as y1 of x without us if it does not have those parentheses present. I'll go to the next, and I got 4 minus 0. And we get the answer right there we want. And so finding that integral, sometimes it's finding the total change if they've given you the rate, or here they're asking you for the average value. That's something a student needs to be able to do. That's one of the 4 required capabilities of the graphing calculator. Okay, the next part asks us to solve when that rate of change, the instantaneous rate of change of C, is equal to average rate of change. And they gave us C prime. And so my hope would be that the student is going to write that equation on their paper and then use their calculator to solve the equation. And so to do that, I'm going to go to the math menu, and the numeric solver, which has always been on the TI-80 series, has always been at the bottom of the math menu. So when I press math and up, it will take me to the numeric solver. I'm going to press enter. And so it's going to give me two expressions. You can see at the top we have instructions, enter equation, E1, expression 1 equal to expression 2. Well, our first expression is C prime. That's 38 over 25 plus, and while the variable's t, as long as I'm in function mode, I can get that x easy with xt theta n. So I'm just going to put x there. And then I'll go down to the next box, and I want to set that equal to the average rate of change. So I'm going to go alpha xt theta n to get a fraction template. And I'm going to enter it in, instead of calculating it in the home page and trying to find that number and store it, I'm just going to type that expression right here. So y1, that's my function c, y1 of 4 minus, and then alpha trace again to get y1 of 0 over 4 minus 0. When I hit the soft key, you can see the soft key is OK, meaning if I press graph, that says OK. It takes me here to this screen, and I am ready to solve this equation. So right now, I need to give it an x value in the range we're solving. We're looking between 0 and 4, so I'm just going to put a 0 there. And for these bounds, I'm just going to say look between 0 and 4. And once I have those bounds, I can go up to 0. And now that it's on the variable that I have, this soft menu key again, solve shows up. And I can press graph, and it solves, and we've got the solution to the equation. But what I like a lot, again, communication, use the technology to reinforce the communication you want to see from your students. That is the expression we want. The variables are a little bit different, but the students are still seeing that same structure. As for part C, as I've said, we've already seen that graph, so I'm gonna press second mode to quit out of the numeric solver. But if I go back to that graph, I can see that graph's leveling off. So I'm hoping from that, just that graph, my students, as good calculus students, even as good pre-calculus students, that they're recognizing that the limit of the derivative is going to be 0, because that graph is leveling off and becoming horizontal, has a horizontal in behavior asymptote. So the last part that I want to talk about with the 84, part D, is another equation. So we're looking at, when does A prime equal 0? And if we have A prime, it ends up, the student solves it, and they get C prime minus 0.1, the natural log of t equals 0. What's really nice is the student thinks about that equation for a second. They can go back to that numeric solver. That equation's still in there, but what I want now is C prime equaling to 0.1 natural log of x. So I've just went ahead and done a little bit of calculus, use the fundamental theorem of calculus to take the derivative of that integral. And I'm setting these equal. I'm going to click OK. And this time I'm between 4 and 36. So I'll set that to 4. And I'm going to put a 4 here and a 36 right there. And so when I go to the x equals, and I press solve, it will give me that value where the derivative is equal to 0. Now, a student needs to be careful with this. They need to know if they have just one candidate. Tony talked about some students using that argument that there was only one critical point. The numeric solver only finds one. So I always encourage my students to make sure they know what the graph looks like when they are doing absolute extrema. So I'm going to press second mode. Oh, I'm going to press second mode to quit and go home. And I'm just going to have my calculator on that same window graph A of t. So alpha trace to graph y1, because that's C of t. And then I'm subtracting an integral minus math 9 4. And it's a little bit bad mathematical notation that I'm going to use X everywhere. But those are one of the things that in the time constraints of a high stakes exam, I'm okay if we use that same variable as we do for the limit of integration. And when I graph this, here comes that next graph. And it might have been good to turn off that first graph, but I can see right now there's only one critical point, and it's right there at 11 point whatever. And so my students can now build that table from those values that they have and answer the question. So that's the 84. Let's look briefly at using the Nspire in the same way. When my students get done with the multiple choice questions on the Nspire, I've given them a document that I call FRQ, and they just open it up. And so if you're not familiar with the Nspire, it has a page system. And right now I have page 1.1, which is a calculator page, page 1.2, which is a graph page. And then I have page 2.1. This is a new problem, new sets of variables. Everything I do in 1.1 and 1.2 don't affect 2.1 and 2.2. So I've set my students up with this file so that they can go ahead and move between question 1 and question 2 however they might like. Okay, and so what I would have my students do first on the free response question is to define the function. And what I like about the Nspire is when I go to define the function, I can use the notation the problem's given. So I've got C of t equals 7.6 arctan of 0.2t. I press enter, it says done. Now I have that function C of t defined in my calculator. I'm going to send my students over to the graph screen and go ahead and graph that function. The key thing you got to remember on the Nspire is that you're always graphing a function of x. We don't want to try to graph C of t. We graph C of x. We get a function that looks like this. And I'm just going to really quickly change my window settings here by clicking on the axis in values. And so I've got 0. I'm going to tab over there to 36. And at this point, once I got those X values set, I can go to the menu and ask for it to do window zoom fit. And I get that same look that I saw with the TI-84. That function is leveling off. So we need the integral, so we'll go back. And again, we want to reinforce communication with the technology. So I'll press Control Divide. Okay. There is a shortcut for the definite integral on the TI-Nspire, and that is Shift plus. So Shift plus gives me my definite integral, and I'm using Tab to quickly move between the fields. So 0 to 4 of C of t, Tab dt, and then Tab 4 minus 0. Whoops, got to tab one more time. 4 minus 0. And this is what I was telling you. Today I was spending time making sure we communicate. This expression is written this way, and then we have that answered. I told my kids it's like watching a movie and they're just like bringing a random character into the middle of the movie, and I'm supposed to know who that character is and how he plays to the climax of the movie and what happened in the beginning. Where does that character fit? We want to make sure that everything is introduced in its right time when our students start communicating their math. So there's our integral expression. Okay. Then part B was to find when C prime of t was equal to the average rate of change. So I'm going to press my menu, and right now I'm live presenting the CAS model. So when I go to algebra, I have a whole lot more than if your student was using numeric, but I'm going to choose the numerical solve here just so that we can see numerical solve and how that would work on the numeric model of the Nspire. So numeric solve, and they gave us C prime of t. And so I've got 38 tab over 25 plus p squared, and that is equal to, and once again, I can just put that same expression in. I can do C 4. Notice that when I type C, it is bold print. That's the Nspire informing me that that's a stored value. It's a stored function over 4 minus 0, and then I put comma P, and it gives me that answer. Once again, right here, we're seeing that same, we're seeing the expression that the student should have written on their paper communicated on the calculator, and part D would be very much the same. But I think it's very good to get your students in a place with their calculator that they're ready for that FRQ. They're not having to clear anything out. They're not worried about calculator, they're worried about calculus. So that's what I got for number 1, Tony. You ready to talk to us about 2AB?
Yeah, absolutely. Great job with that. I tell you, one of the highlights, I think, of what Dennis shared with you is that numeric equation solver for the TI-84. It's a way that you could really, I guess, show students that as TI-84 users, it's not all about the graphical realm, and that you can see that analytic realm really well with that application. So we really encourage you to give that a try and show that to your students. Now, we did a really thorough job there with AB1. We're going to kind of gloss over here AB2 just a little bit. I've got a couple of things here that I think you're going to find quite interesting with the philosophy of the scoring here. So our first part here, after having the shaded region R bounded by the graphs of F and G here, we wanted to find the area of R. And so our first point is just going to be a form of our integrand. Now, a lot of times people get kind of confused by what does form of the integrand mean? We'll take care of that here in a moment. And then, of course, the answer to 3 decimal places would be our P2. Now, when we look at our scoring notes, that form to earn P1 is presented for basically knowing to subtract those 2 functions in some kind of an environment. Now, of those 4 options, I believe 3 of them are correct. If I'm not mistaken, I believe the third one, right? The F minus G would likely cause some problems, maybe a negative answer, but we're going to still be okay with that because it does have that form of the integrand. Now, of course, the student is not going to be able to earn P2 if they present that negative answer. And then P2 is earned with the correct answer, even without supporting work. You might find that surprising, but that sort of naked 5.137 floating around does indicate to us that the student knew some calculus, and we're not going to be so stringent upon that supporting work for that particular answer. There's going to be other places on this exam where that may not be the case, but here it's fine. And you'll notice that this particular response here with the integral of F minus G with our correct answer, that's going to earn both P1 and P2 because the student was able to recover in that case. So obviously, having the F first is initially bad, but we're going to sort of kind of hold judgment to see if we can still earn P2 if they don't present a negative answer. Yes, it is incorrect linkage, but it's not going to be considered in scoring. But of course, you can make your bar higher, and we encourage you to do so. Now, our base, R is the base of a solid. For the solid, at each x, the cross-section is going to be perpendicular to the x-axis and a rectangle of height x. Find the volume. So our form of the integrand is going to carry our P3. Notice it is a x times our g minus f, and then our answer 7.704 or 705. So form of integrand, well, that P3 is going to be earned for a definite integral as long as it is a product of 2 non-constant factors. And one of those factors has to be one of our 3 pertinent things. So if you think of all the different permutations that could go on in a student's head there, that's going to be enough to earn P3. The philosophy is that the student knew what a rectangle form for area looked like so that we were going to be able to integrate that area to produce the volume. Now, the presence or absence of the differential dx will not be considered in scoring P3 or P4. Stand by for that here in just a little bit. And then P4 is going to be earned for the correct answer, again, with or without supporting work. And a lot of folks had perhaps using a CAS calculator and had the exact answer in that case. So again, if you look at the incorrect presentation of F minus G, which we're not real thrilled about, the student was able to resolve that error, call the answer 7.7045, even with that linkage error could earn both points. Now in part C, we're going to write but do not evaluate an integral for the volume rotated around y equal -2. This guy carries 3 points. Our first point is the form of the integrand. Second point, P6, is the integrand. And again, I know it's very easy to get confused by those two ideas, so we'll break those down for you here in a second. And notice P7, limits, constant, and differential. Did that say and differential? So let's take a look at the notes here. So P5 is earned for a definite integral that has an integrand of the form some kind of a function squared minus a function squared, whether it's in absolute values of not. Now, one of those two functions, one of those pieces, one of those r's has to be either correct or be the difference between g and a non-zero constant, or one has to be correct and the difference between f and a non-zero constant. Now, I know that might seem kind of confusing and you might have to digest that a little bit later when you get access to this, but I think the philosophy here is that there were a lot of students who sort of erred on the subtraction of -2 and maybe didn't turn that into a +2, but it stayed as a -2. And those students really were into our problem. They were into our idea of the integrand. They just didn't have the correct integrand. So we wanted to reward them with the P5, but they were going to have a very difficult time from that point on earning anything. P6 is earned for our correct integral, as you can see. If a student were to reverse those two terms, the f of x plus 2 squared coming first, we're going to be okay with that. We're going to wait and see how they resolve that to get the third point P7, however, but that is close enough to our washer method that we're testing the students over. Now, if you look there at the bottom there, a response of pi times the integral expression there, that would earn P5 and P6, but it would not earn P7, right? If you kind of take a good look at that, it's because of that error, you know, we're not going to overlook that transposition to get that final point P7. To earn P7, a response is going to have to earn P5. And then finally, this might be one of the more interesting things, for us to think about here. Sorry, I wanted to go back. That dx is sort of a non-negotiable in this problem. So I want to make sure that that's very clear. This particular problem did enforce the differential being there, and that's kind of rare on the AP exam. And so again, hold your bar very high and really expect students to write that differential, because there are going to be times that it certainly matters. And then finally, for our part D, it can be shown that G prime is equivalent to this sort of trigonometric expression. Let's find the value of x at which the tangent line is parallel to the line tangent to the graph at G. So essentially, to earn the P8, we're just going to show that f prime is equal to G prime. We can do that very softly and subtly, as you're going to see. The answer is going to carry the 9th and final point. And for that P8, a little clarification, a general statement like f prime of x equal G prime of x would be just enough to earn that. They don't have to actually physically write out the specific G prime. And P9 is earned for the correct answer with or without supporting work. So again, we're seeing a little softness on the supporting work on calculator active questions, but by and large, that probably is not going to be the case as the students move into the non-calculator part. So, and this guy here had an average of 4.1, a little bit better. It was interesting to see an area volume question show up on the calculator active, as we haven't seen one in that particular place for a few years. Dennis, what do you got?
Well, I just want to mention that in my time as 8 years as a reader, one of the frustrating things for me was you would open a book and those linkage errors and those copy errors would leave you with a book with calculus done in it, but it would be a 0. And then you go to the next book, which would be a blank, and that student who didn't even take time to write in it was getting the same no credit as students who had done some calculus. So I really, as a teacher, while I want to emphasize this communication idea, I really like this idea that we're letting students who are doing some good calculus work, who are showing a little bit of understanding of the problem, get some points. So
Very well stated. And that, I think,
Yeah.
is the true motivation of the entry point. Very good.
So we got what I want to do here with this question is talk about the Nspire premium teacher software. And I know some of you are 84 users and some are Nspire users, but the TI-Nspire teacher software is an essential teaching tool. And what's great is that TI will make it available to you, a license available to you, even if you're teaching with the TI-84. I got an email this week from TI that says, hey, 3-year a 3-year license to the software is waiting. You can email your ETC or you can work through that email and they will give you a 3-year license to the teaching software, even if you're an 84 user. Thank you, Mike. So we can see right here, all I have is a little problem and I've got it set up so that I can grab that point, because what I want my students to see is that we're just adding up the area of those rectangles. I'm really emphasizing when I do area and volume, the slice of that area as a rectangle, not necessarily that I'm doing a definite integral minus a definite integral, but I'm adding up areas of rectangles, because that's going to pay dividends later, because here we have that volume of the cross section. Okay, and over here I've got that region graphed in 3D space, and you can see I can grab that and move it so we can see a little bit of depth there. And I'm just going to move the slider up across the top and it builds that nice little volume for me. Sometimes my students are like, oh, what will that volume look like? And I'll humor them for a second. Okay, it might look like some kind of jello mold or something. But what I'm really interested in is, what does that cross section look like? And being able to grab this, and so they can see that the base of this rectangle is just that same rectangle that we saw when we did the area. But what I really liked about this problem, the fact that the height of the rectangle is the distance, you can see that rectangle gets shorter and shorter and shorter the smaller x is. And so we can go through this and demonstrate to the student that you can get this. And so afterwards, Mike said you will be able to get these files. And so there's this file, but there's also a general file where you can teach uniform cross sections just like this. Here is the rotation problem. And one of the things that one of my friends likes to make sure of that her students do is that they sketch this reflection over the line of rotation so that they can see what that reflection looks like. But one of the things I told you, I humor my students with letting them see what that solid looks like. And so I'm like, okay, this is what the solid looks like. But I don't really care what the solid looks like, because I've emphasized that rectangle. And instead of rotating the whole solid and slicing it, we're just going to rotate this rectangle. Whoops, I want to rotate it from down here. So as this rectangle rotates, let me turn your perspective a little bit. And you can see that as it goes around, we get what, when we were calculus students, is called a washer. My students don't know what washers are. They don't go to the hardware store very much. But when I turned this yellow, they immediately knew they were looking at a pineapple slice. And so in my class, we pass out pineapple slices and calipers, and they measure the volume of that pineapple slice. And so we can start talking about the outer radius and the inner radius and finding how we have the area of a big circle minus a little. And then I can even grab this so that I can see that that radius, big R and that little r, are both going to depend on where I slice it, that value of X. And then at the end, there's even a page where we can look at these two functions and play around and say, okay, where are those tangent lines going to be parallel? And try to tweak it. But if I click it one more time, we're going to see that it's right there at the intersection of those derivatives. And so I think it's really important that students get a good visual representation of the calculus. That we're not trying to go looking for things. We want to do it in an environment they can see, and that one that also will promote that communication as well. So Tony, you got just a little bit of time to talk about.
Well, I tell you what, I think I'm just going to introduce it, and then I'm going to send it right back to you, because
Okay.
your file over this is too good to not share. But just
Okay.
really briefly, I wanted to show you what our BC question of the evening looks like, BC2. Now, for those of you who have been around the block for a while, Dennis and I talked about this the other day. What did Dennis at 2019? Is that the
Yeah,
last time?
2019, last time showed itself.
So does a FRQ. So we thought that it had gone by the way of the dinosaur, but boom, it's back. And I think the parts of this polar question were very standard. And so again, just in a few weeks, you're going to have access to all of the wonderful information about this particular problem. But just looking at the parts, we were finding the rate of change of R with respect to theta. And so just a simple 1-point answer with setup. This is a situation where the student would not earn credit for just the simple numeric answer. They had to say something to the effect of a dr d theta or an r prime. Notice down here, they could do so with incorrect communication. In other words, they spoke what we say, generally there instead of specifically. So that was one of the things that I wanted to illustrate there, that not everything is just this really easy entry point where the student can just write an answer. Here, we needed to see just a little bit of work. And then in part B, the students were finding the area of the region that lies inside the curve and outside. And so there were points earned for the setup and a point earned with a true correct integrand there. Perhaps we can, you can have you guys go into a little bit more detail with this. I'm going to move on just very quickly to part C, just to illustrate that if this looks familiar, the slide, it's because it probably does. It's another global argument. And so the students on the BC exam had 3 opportunities to express their knowledge about the global extrema there. ABBC4 would have been another one. And then just very quickly here, just looking at the average of this problem before I turn it back over to Dennis. BC2 had a 3.1, which is not too surprising that it was the lowest among the BC6 questions there. So Dennis, let's take a look at that file if you don't mind.
Let me share that file. I will say that one of the things that you notice is part D is essentially multiplying A by by a number. And one of the things I always tell my students, whoops, I'm sorry, sharing the wrong screen. One of the things I always make sure my students know is if you don't have an answer and you need it later, make one up. Make one up for A, and you'll see in the scoring guidelines when they come out, if you had an answer for A and multiplied it in part D, you would have gotten that point. So for this problem, one of the key skills I want my kids with polar graphs to be able to do is to take this Cartesian curve of R against theta and understand what's happening as it gets traced out. And so right here, I can trace out that Cartesian curve. And as it does, they can see the exact changes in that polar curve below. And what I like is you can see where the 2 curves intersect in the Cartesian graph. That is where my region is. I think a lot of students had issue with this is because they were like, okay, they were trying to subtract and add different regions in different places. But to get it, all they have to do is look at the area that starts where the 2 curves intersect here and finish here. And then part C, which was talking about that x coordinate, well, this is still the graph of R. The x coordinate is just R cosine theta. And so one of the things we want to do as teachers is pose that purposeful question. And I might just say, okay, this is R from 0 to pi over 2. If I multiply that by cosine, what's going to happen? Hoping my students know that cosine is somewhere between 0 and 1. Okay, starting at 1 and going to 0. And so if I put cosine on there, we can see, oh yeah, it's going from exactly the graph down towards 0. But right there, that's the x coordinate plotted in this. But that's the same as that length of that line. And we're looking for where that is going to be at a maximum. And that maximum occurred right where that derivative that the problem gave us is equal to 0. And so giving students some visuals about the relationship between the curve graphed on a Cartesian graph, because a student shouldn't be switching modes during the AP exam. They should be staying in that function mode and knowing how this relates to that polar graph that the College Board and the Test Development Committee has always given us. And there's a general polar tracing file that you guys are going to get for cardioids and limasones in Rose curves if you're interested. All right, that's what I've got for B. I mean, for
All right.
2BC.
Sounds good. Michael, I think we're going to send it back to you.
Awesome. Thank you, guys. We are giving away to one lucky winner a graphing calculator of their choice, and tonight's lucky winner is Bernie Robidart. So, Bernie, congratulations. Start thinking about which graphing calculator you'd like to receive, and I'll be reaching out to you soon to get some information.
Congrats, Bernie.
Speaking of information, to receive the documents and the certificate, go ahead and click the links in the chat window. And if those links aren't working for any reason, hang tight. You'll automatically get a follow-up email in a couple days with links to the chat, the certificate, the documents, and the recording. And if you're watching this on demand, copy that link into your favorite browser to receive your certificate. So huge thanks to Dennis and Tony for everything they put together tonight. I think I personally got a lot out of both of you, so thank you so much for everything. Dennis, thanks for shooting your email in there. Huge applause and thanks to both of you. And thanks to everyone for showing up tonight. We really appreciate it. Have a great night.
Hope you have a great calculus year.
Have a great year, everybody.